the best way to understand momentum or physics in general, you got to start doing some examples. We're going to do some important momentum examples. I'm going to start with this one right here. And what I want you to picture is this. Picture like you're on the bumper cars, right? And right before the collision, somebody takes a picture right before the two bumper cars collide. Then immediately after the collision, you take another picture to describe the cars right after that collision. When you're doing momentum examples, we're going to take a snapshot in time of what's happening with your objects before a collision and then after a collision, okay? And the goal is, if there are no outside forces, just like we said, PI should equal PF, then when we do this, it actually works out pretty nicely. So the first example, it's two blocks they're going to hit and they're going to bounce off each other. I've drawn a picture here, and you know what? I'm not going to give you any numbers. I'm going to use all letters. Sorry, I got feisty. I took all the numbers, most of the numbers away. So here's the picture. Your momentum initial, this is like a snapshot. As a camera. We had cameras before phones. And so you took a picture. This is some bumper car, mass M, moving at 3v naught to the right. And some other bumper car, it's got more mass, 2m, and it's moving to the right at v naught, just like that. Now, I said momentum's a vector, and a really, really helpful thing to do, get that coordinate axis going back right there so you can tell the AP graders to the right is positive. If I get a negative number, that must mean it's going to the left, okay? So before the collision, we want to ask ourselves, how much momentum was in our system? So all we do, we just add up the units of momentum. This has a certain amount of momentum. This object has a certain amount of momentum. And we know that the initial momentum should equal the final momentum. Okay? I'm going to try to do the fancy teacher trick of using 2 sheets of paper. And one little thing. Oh, actually, I'll say this right now. So that's before the collision. So your friend was sitting there before on the bumper cars, took a snapshot. Boom, that's what was happening. After the collision, momentum final. And I'll throw some... Get lazy with my vector arrows. Put them on here. Vector arrows, just like that. After the collision, your friend observes that the car initially here, that one, the mass M car, is now moving to the left with a velocity negative v naught. This car right here still has the mass of 2m, but you want to figure out, hey, how fast is that car going after the collision? Okay, so just to recap, this is what was happening before the collision. This is what's happening after the collision. And now we're just going to say PI equals PF. I like to make a little table. I say PI should equal PF. There are no external forces. Our system is this 2-car system. I just put a little dash, dash, dash. That is our system. There's no outside force pushed on this car. Or no, I'm going to say no friction. Let's just say that's our system. So PI should equal PF. So, all right, our initial momentum. This object has a mass of m and a velocity of 3v naught. So how do you find the momentum of that object? To find the momentum, you just take m times whatever the velocity is. Okay, so my first spot right here, my first object momentum, it has a mass m and a velocity of 3v naught. Okay, initially. But before the collision, this object also had momentum. This object, this bumper car, had a mass of 2m and it had a velocity of v naught. So the total initial momentum of the system is the sum of the two momentums right there. So you're like, okay, this object, the first one had a mass m, velocity 3v naught. The second object had more mass and was moving slower, but that is the total momentum of the system to begin. And we know whatever the momentum at the end is, it better equal that. And let me just do some math. That's 3mv naught plus 2mv naught. So if you do some math right there, you should get that if you combine like terms to be 5mv naught. So now here's the thing that bugs some people. After the collision, you know the mass of that first car, the mass didn't change. With rocket ships, when rockets burn fuel, they're losing mass, so their m drops, and so that's where you can change mass. But with bumper cars, your mass better not change, because that means something flew from your cart or something added to your cart. That'd be weird. Valley Fair wouldn't like that. Okay, so you're gonna add up the momentum after the collision. You're taking a snapshot after the collision. That was me taking a picture again. And we know this object, this first one, had a mass of m and a velocity of negative v naught. Now here's an important thing. It was going left. Left is negative. You got to put the negative in there. So its momentum is a vector. Plus, this object still had a mass of 2m, but we don't know how fast that object's going, so we're just going to say v final. Oh, look, I made it red to kind of make it cool. We don't know what it is. It's like it's on fire. I don't know. But anyway, so here's the deal. We know everything. Mass, velocity, this mass, velocity, this mass, this velocity, this mass. We don't know the velocity of that last object right there. So you're just going to go through and math it, simplify some things, and you get 5mv naught, negative mv naught. We're looking for vf right there, so add that term over. 6mv naught equals 2mv naught. The m's go bye-bye. And you find out the final velocity Oh, you got to divide by 2 there. 6 divided by 2 is 3 v naught. So that bumper car on the right is moving to the right with a velocity of 3 v naught. Okay? And sometimes that doesn't make sense. I don't know if I picked the best letters to represent things, but you're really just saying my PI has to equal my PF if there are no external forces on the system. Just a note here. PI equals PF, which means your impulse, there's no impulse to the system. And think back. Remember we did energy stuff? EF minus EI equals 0 joules if there's no outside work. Well, PI equals PF if there's no outside impulse. And one little thing, I know with energy, I like to do things like EF minus EI equals 0 joules like that. And some people are like, well, Laurent, why don't you just say EI equals EF? I don't know. That's a personal preference thing. I like to do EF minus EI equals 0. And I say, oh, it should equal 0. And if it doesn't, then that must mean there is some type of work done. With momentum, I do like to set them equal. So I'm not totally consistent. I like to say PI better equal PF. And I'd like to tally them up left side versus right side and look at them like that. That's just a preference thing because momentum's a vector. So that's a real quick example, but just to recap, we summed up the momentum of this object plus this object because that was our system that we defined right there. And we said PI better equal PF right here. So then we said, okay, let's sum up the momentum at the end. And we said, oh, we know the mass and the velocity. We know the mass. We didn't know the velocity. So we said PI, if it's true that it equals PF, we went through, we said, we had this much momentum to start, this much to finish, and we did boom, boom, boom. We figured out in order for this to be a true statement that the momentum initial equals final, that second block has to be moving 3 times v naught. Okay? So that was a good example of a collision, and we've never done anything like that before. So if you see a collision, momentum is the way to go. That was blocks bouncing off one another. You know what's going to happen next? We're going to do a situation where the blocks hit, but this time they stick together. It's actually the same numbers. Example 2, we're going to set up the same situation. I'm going to try to get this done quickly. But you got this block, mass. Maybe they hit so hard that in Valley Fair is not going to like this. Maybe the bumper cars hit so hard they stuck together. First situation, example 1 today, they hit, they bounce off. This situation, they're going to hit and stick together. This bumper car is cruising to the right, 3 v naught again, mass m. This bumper car is cruising to the right again, mass 2m. And you know this one's eventually going to hit it. This one's going faster, right? This is your PI. This is your system. Your initial momentum is that system right there. That unit plus that unit. You could do it with a third bumper car, a fourth one, or 3 train cars, whatever. You're just taking the total momentum of your system right there. In this case, there's 2 bumper cars in our system, okay? And here's the picture at the end. They hit and they stick together. Now, if this mass was m before and this is 2m, they're going to hit and stick together, so they're going to have a combined mass of, you guessed it, 3m, okay? And the question is going to be, all right, they hit and stick together, how fast are they going? See if you can do it. Set your PI equal to your PF, and one thing, we know we can do this. PI better equal to PF because we're not saying there's any outside forces. There's no impulse. Remember, when I say impulse, that's a force for a certain amount of time. There's no outside force acting on the system. Let's see what we can do. PI, we're going to play the same game, right? That first object had a mass of m, a velocity of 3 v naught, boom. The second object had a mass of 2m and a velocity of v naught. So we add that together. You still get your 5m v naught initially. On the AP test, I think sometimes they'll do stuff like this. So keep in mind, if it's the same setup, you should have the same initial momentum that we just had in our last example because it's literally the same setup. And the only thing that's a little weird, you're not going to have 2 terms anymore on the right-hand side of the equation because you're just going to have 1 term because now it's like 1 unit. They're kind of slapped together. So you have m plus 2m, and they have a common velocity, just like that, okay? And we get 3m times vf right there. M's go bye-bye because you have m's on both sides. And you get 5/3 v naught. So the combined velocity of that unit right there is 5/3 v naught. And let's see if that makes sense. So that's a little, what is that, 1 2/3, 1.66 repeating. You know they're going to be going somewhere for a velocity in between kind of that region right there. So I can buy that 1.66 is their velocity because it's got a bigger mass. So to maintain momentum, it can't have quite as high a velocity. Okay? It can't be cruising at 3 v naught because if all of a sudden it was that they hit and stuck together and it's cruising at 3 v naught, it'd have more momentum than you started with. So we made the big assumption, and it was a pretty fair assumption. PI was equal to PF because and if you want to look at like P final minus P initial equals 0 Newton seconds, if you want to think about it like that, there is no impulse. There's no change in momentum because there is no outside force, so there will be no impulse. Okay, so keep in mind, we said Pi equals Pf, which is the same as saying Pf minus Pi equals 0. And the reason we can say that is because there is no outside force acting on our system, which means there's no impulse. And what I'm really trying to tie back to, remember, force times time, that's impulse, a change in momentum. We're saying there was not a change in momentum of our system as a whole. Just say Pi equals Pf. This was our system at the end. This is our system at the beginning. The momentum here should equal the momentum here as long as there's not an outside force. Okay, so there you go. Those are some 2 more complicated examples. Let's see if we can get this one done. Example 3, astronaut. You're like, Laurent, you've never drawn a picture that good before? I spent a lot of time on it, to be honest with you. So that's Mr. Laurent, astronaut. I have a hammer in my hand. The Laurent space station, apparently I established it in 2018. Just like that, is right there. I got to get back to it. Now here's the deal. This is a classic collision in reverse. That's me at rest with a hammer. And my momentum initial Pi would be 0, right? Because we're at rest. And I want to get back to my space station. So if I want to get back to my space station, which direction should I throw my hammer? I should throw it to the left, because that will have negative momentum, and that will force me to go to the right to counteract that negative momentum. Okay? Now, just big picture stuff. That hammer has a very low mass compared to the mass of a Laurent right here. So if I throw a low mass object with a high velocity, that means my big mass will move at a low velocity that way, just to conserve momentum. But let's prove it to ourselves right now. Lots of words, I apologize. Just write down your givens. Mr. Laurent is at rest in space. He needs to get back to his space station. If he throws his hammer left at 20 meters per second, 44-ish miles per hour, how fast will he move to the right? Oh, sorry, that messed me up. The mass of the hammer is 10 kilograms. How fast will he move to the right? Assume he has a mass of 100 kilograms, 220 pounds. Pi equals Pf. Let's see if you can do it. And hit pause and try it out, and then I'm going to walk you through at the last minute of the video. Okay? Pi, really easy. There was no momentum to start, so there should be no net momentum at the end, right? Mass of the hammer was going 0. Mass of the is going 0. So at the beginning, you have no momentum in the system. At the end, you better have no momentum. You're like, Laurent, how can I have no momentum? The hammer's going to have negative momentum. Laurent's going to have positive momentum. It'll sum to 0. Let's see if this works. So you should have 2 terms over here because the hammer's flying to the left. So the mass of the hammer times its negative 20, because I threw it left. According to my coordinate system, negative is left, plus the mass of Laurent times my final velocity. You do the math. 0 equals that right there. I add that over, divided by 100, and you get that I am moving at 2 meters per second to the right. I know I'm moving to the right because my positive answer at the end. And they'll ask you all sorts of funny things. So the question they might ask you is, once you know the velocity is 2 meters per second, they could ask you all sorts of questions. They could say, if he's 100 meters away from a space station, how long will it take him to get there? And then you got to go back. You got velocity. You got to go back to kinematics land. You're like delta x equals 1/2 at squared plus v naught t. And you might be like, my old tools. Your old tools are never going away, and that's what's awesome about physics. The one thing that's a little weird, if you're floating in space, let's assume there's no air resistance and you're not slowing down, your acceleration is going to be 0, because once that hammer leaves your hand, you're going to go at a constant 2 meters per second the whole time. So acceleration would be 0. Let's say you're 100 meters away, boom, and you're moving at 2 meters per second. I know I said v final there, but the final after the hammer leaves your hand is your initial for the rest of the trip, if you can picture that. So if you're doing this, you'd say, hey, all right, 2 meters per second, I'm cruising 100. It takes me 50 seconds to get back to my ship. Okay, or station. That's about as tough as they get for a while, and we're just gonna do a whole bunch of practice. And I want to throw these 3 quick examples in just so you got a chance to see what types of questions you'd be asked in your homework. I hope that helps. Thanks for watching. If you have any questions, just send me a message. And yeah, momentum's a vector. You use it when there are collisions. This would be a collision in reverse because 2 things whoosh, exploding apart. So pretty cool. Have a great day.